Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Welcome to an integrated Math 2 review on a bigger expansion on exponential functions. Some more with the quadratics and complex or imaginary numbers are popping up during this, as well as what I'm going to kick off with are graphing exponential functions, and also simplifying exponential expressions. I don't know if I made a video on a review on exponential expressions. I gotta look back. I don't think I did, but I did do a Q&A Power Hour video that covered it, just in case any of my students did have that. Just a heads up, I'll be doing a Q&A Power Hour video this weekend as well for my Integrated Math 1 and 2 classes, as my Integrated Math 2 is covering and testing next week on the things I'm talking about right here. Graphing exponential functions, using exponential models, I didn't mention that, exponential growth and decay with word problems, we'll look at that. Some quadratic equations where we solve for non-real solutions. I don't know if any real solutions pop up. I haven't done these problems yet, so we'll look at those. And what did I say? Quadratics. Some more on imaginaries, doing some simplifying expressions on imaginaries, and oh yes, of course, simplifying exponential expressions with all these different properties and such. Now this is a bigger review. There are 32, there are 32 questions. Some, like this number one I'm looking at right now, has parts A through D. They are all 4 different problems, but it's all under number 1. But there are 32 questions total. So I do want you to know this is going to be an expansive review. Now, I don't plan on being here all night. I still have another video to make for my Integrated Math 1 folks. And as this practice test is for my Integrated Math 2 folks, I don't want them to be sitting there doing this the entire time, but of course I want them to learn something. But I think I'm going to come through this with more of an approach of what I've taught is what you're expected to hear. So if you're coming from somewhere else in the country, or just from not underneath my classroom, some of this stuff may be new to you when it comes to how you hear it. So I hope that the stuff that I impart for you is a different way of learning how to do it that may be helpful, or it may just reinforce a way that you already knew how to do it, and that's fine as well. But without further ado, guys, I'm going to go ahead and get started. Like I said, although this is a very young night for me still, I have a lot to do. So I'm going to go ahead and get started, and we're going to kick it off here with number 1. And there's a set of graph axes here behind me. You know what I'm going to do also, by the way, before I do start this thing, guys, is of course in the description section down below, there will be timestamps for each problem, including number 1A and number 1B. They'll all be separate. And I'm going to give you a PDF of this sheet that I'm giving you here, as well as a PDF for graph axes that look just like this if you'd like to print them out. Okay, so that'll be set for you guys in the description section down below. Okay, let's go ahead and get started. Number 1, graph each. Give the domain, range, and describe the end behavior of each question here. State whether the function is experiencing positive or negative exponential growth or decay. All right, so with this one right here, y equals, well, actually with any of these here, all of these are coming into the form y equals a times b to the x power. This is an exponential function where a and b represent parameters, and they are parameters that you can use as numbers to actually help form your graph. So I am actually going to graph these without a table. If my students may graph using a table if you'd like, you may graph using a table if you'd like, which means you need to make sure you know how the zero exponent works, how negative exponents work, and how order of operations work. I'm going to do it without a table. That doesn't mean I won't show some calculations with you here, especially with the fractions, but here's how we can do this. Every a value, without any vertical translations, any a value here, or horizontal, any a value will represent your y-intercept. It'll represent the y-intercept, which of course crosses at 0, a. The b value is known as your growth factor. It can also be called your decay factor, all depending on whether it's actually growing or decaying. So growth or decay factor. Okay. This will tell you, because it's influenced by x, this will tell you every time I increase x by 1, I will multiply by that b another time on my previous y value. So you'll see that take effect. That's how I'm doing this without a table. Just like y equals mx plus b form. Every time I increase x by 1, rise this, run 1, rise this, run 1. But this isn't adding a number. This is multiplying a number. And then I'm going to talk about a feature on the x-axis with no vertical translation called the asymptote. Okay, let's officially get started on number 1. Y equals 3 times 3 to the x power. Now, first of all, you cannot multiply 3 times 3 and call this 9 to the x power. They're not the same thing. order of operations dictates that we have to raise this to the x power first before we multiply second, at least as far as computing. But of course, I'm not using a table. I'm just letting you know that would be different. Okay, so with this one, the 3 here represents the y-intercept. So I know that I have a y-intercept that is at 0, 3. This 3 here is going to be my growth factor. It is a 3, which means I will be multiplying my previous y value by 3 each time to get my new y value every time I increase x by 1. So if my y-intercept is at 0, 3 for number 1 here, and this might help us for our scaling, every 5 I go up, I'm going to put kind of a little, I'm not going to put the number 5, just a little tick mark. That just lets me know that I went up another 5 there, so I can know where I'm going all the way up to. I think I made this thing go all the way up to 27. Yes, I did. So 5, 10, 15, 20, 25, 26, 27, which is good for, I think, this problem here. All right, so for number 1, I can start at 0, 3. This is my y-intercept. That's where it crosses the y-axis. That is one of the points on this graph. Every time I increase x by 1 here, my y value will get tripled. Now, if you're doing vertical translations, you have to know something about a word called asymptote. I'll be talking about that, but you won't be tripling the y value. You'd be tripling your distance from the asymptote. Our asymptote's on the x-axis, so this is 3 away. I'm going to triple that number. Triple 3, I get 9. So when I increase x by 1 here, I'm going to look at 9 for y. That's my next point. And if you plug in 1 for x, you'll get 9 for y as well. When I increase x by 1 again, I will be tripling y again. This is the behavior of an exponential variable. This x here makes that happen. Tripling 9, I get 27. And 27 is all the way at the very top. Good thing I created one that went to 27. Then again, I probably created it that way, so I could do that. Now, you don't just have to go to the right, you can also go to the left. And, you know, this thing about this graph is you can see it's only first and second quadrant. It's very tall for a reason, as you can see. But there's also this idea behind the fact that it never becomes negative. No matter what I do, I'm going to be multiplying by 3 going to the right, and going to the left, conversely, I will be dividing by 3. If I take a positive number divided by 3, it's still a positive number. It gets smaller, it gets closer to 0, but it's still positive. So what happens when I take 3 and divide it by 3 here? I get 1. So when I decrease x by 1, I divide by 3, and 3 divided by 3 is 1. Well, what if I take that 1 and divide it by 3? 1 divided by 3, everybody, that is 1/3. I'm not going to get to decimal form with you here. Let's just leave it as a fraction. That's 1/3. Where's 1/3? Well, it's a third of the way up from 1. It's about right there. I don't know. Give or take. I'm roughhousing it at this point. Roughhousing it. Now what's next here? As far as points that you could fit, this is getting a little borderline. We're not going to be perfect, so that's okay. But what if I took 1/3 and divide by 3? You know, at some point it's easier to just say multiply by its reciprocal. 1/3 times 1/3. See, 3 is 3 over 1. When I flip it and multiply by its flip, I think someone tells me keep flip change. I'm not sure how they say it. Flip, keep change. I don't know the actual thing. I just know you multiply by the guy's reciprocal. And you get 1/9, which gets closer and closer to 0. There's 1/9, and then eventually you're hitting 1/27. I mean, you're getting really, really small there. Super close to 0. But once again, you never actually truly hit 0. Kind of neat. And you start approaching it. And that's where we're going to be talking about the domain and range and the end behavior. So as I draw this asymptote here, this asymptote, this dotted line on the x-axis, is my way of saying that I will never touch that line. I ask my students to draw an asymptote anytime that they can, unless we're doing a distance learning test, you know, something on the computer. But I ask them to try and draw the asymptote. I want to make sure they know what it is, what it means, and what's happening. Now, these drawings will not be perfect for me. It's really hard for me to do this very tall with my computer thing, but I'm drawing a curve that connects, that connects these dots right here and that exponential growth. And man, it takes off super fast, guys. It takes off super fast, and that's basically how these things work. You triple the previous amount, and boom, 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 there it goes. Now, I draw arrows at the end to state that this thing is going forever. It's not just going forever up, it's also going forever right. Remember, just because it's going more sharply upward doesn't mean that it's not still going rightward. And that's where we have to answer some questions here. One of the first questions is giving the domain and range. So the domain and range on part A, and trust me, I'll be going faster on the other ones now that you've kind of heard the beginning parts, but I have to talk about fractions and negatives as well. The domain and range, domain asks, what values of x does this graph hit? And the truth of the matter is it hits every single x in the world. It goes forever left, it goes forever right, and you're going to see all of them. So you can put something like the symbol all real numbers Or you can say you're going from negative infinity to positive infinity on x. We never actually hit infinity or negative infinity. That's why we don't put the equal signs there. There's also an interval notation. I'm going to refrain from it from now. I'm asking my students to go back to inequalities for now. But you can also use interval notation. Either or works there for domain. And the range asks, what y values do we hit? Now, what I've mentioned on this one before is no matter what, if I take a positive number and multiply it by 3 or divide it by 3, two things won't happen. It will never become 0, and it will never become negative. Now, one thing will happen. It will always stay positive, and here's the thing. It'll hit every positive number in existence as long as we span across the all real number domain. So here, y must be a positive number. Not just must be, but it hits every positive number in the book. Y is greater than 0. Those are my range values. You'll see every y value in existence on here. Excuse me, every positive number for y. All right, that's the domain and range. The end behavior, my face kind of gets in the way of this. I'll go to these problems later, so let me get rid of the other problems here. The end behavior asks, how is this graph behaving as we look forever to the left and forever to the right? We do know that it hits an all real number domain, so it goes forever left and right. Just the question now becomes, basically how is y behaving? The end behavior here. And the syntax will go as follows. I'm going to write as x approaches infinity, which is a way of saying as x goes forever to the right. As we start looking at points that go forever to the right here, forever to the right, I am asking what the y values are doing. As x goes forever right, what's y doing in this case? Well, when we are looking forever right this way, it looks like it's shooting up forever upward. So y is approaching positive infinity in its own right there. And as x approaches negative infinity, geez, I've spent a lot of time on one problem, guys. This might be a very long video. As x approaches negative infinity, y isn't actually approaching negative infinity. One more time, y does never become negative, and it never becomes 0. It approaches 0, though, and that's what we're talking about with end behavior. We're saying, how is the graph behaving? And right now, there's a word, it's called converging. It's converging and getting closer and closer to 0. Never equals it. Never equals it, just like it never equals infinity, but it does start to approach 0 as we go forever left. You can see that. As we go rightward, we go forever up. As we go leftward, we go forever closer to 0. As we go squaredward, I don't know, something else happens. All right, is this function experiencing positive or negative exponential growth or decay? The graph is above the asymptote here, not just above the x-axis, it's above the asymptote that's on the x-axis. Therefore, it's a positive graph. Whether it comes up on this side or whether it goes down this way, it's positive. So this is positive. Now, the question becomes whether this is exponential growth or decay. The growth occurs as a result of, as we go forever right, the graph separates itself from the asymptote. It goes further and further away from it, and that's what we're seeing here. This is positive exponential growth. Decay would be going this way as it gets closer and closer to the asymptote as we go to the right. Because we think of the right as kind of as time goes on, and we're going to be seeing word problems, I think, right after this, A through D, right here, in doing that same kind of thing. So this is called positive exponential growth. And spoiler alert, I think all 4 problems here experience any matter of positive or negative in growth or decay. So you'll be able to see what all 4 of them look like. So that is letter A, and I know that was a long time, but hopefully you learned something with that one, so that can help you do the others. I'll do the other ones significantly faster now that you know what domain and range means, now that you know what the syntax means for these, now that you know how to multiply by a reciprocal, and what the y-intercepts and such are. So there's a lesson into it. I hope my students learned something from it. Let's move forward. All right, letter B here. Do all the same things. I'm going to start with the graph here. Y equals 4 times 1/2 to the x power. So again, tall graph here. I'm going to start with the y-intercept of 0, 4. Okay. Now, this one has a growth factor of 1/2. It's better probably known as a decay factor. I think that's also a way of just knowing that it would be exponential decay. Now, one thing I didn't mention on the last thing here, and I will here. When we talk about growth and decay, I'm going to include something else that I didn't include last time. So I hope that's okay. All right, guys, I'm going to start at 0, 4. Let me do that scale again. 1, 2, 3, 4, 5, and 10, 15, 20, 25. All right, I'm going to start at 0, 4 right here. And unlike last time when I multiplied by 3 each time, meaning I tripled my things, now I'm going to be multiplying by 1/2 every time x increases by 1. And multiplying by 1/2 is another way of saying divided by 2. So that's why this thing has a decay, because it's shrinking over time. It's not negative, but it's shrinking over time. So this is 4, and then when I increase x by 1, I got to multiply by 1/2. And 4 times 1/2 is 4 divided by 2, which is 2. So there's another point here at x equals 1, y equals 2. Now I'm going to take the 2, when I increase x by 1 here, I'm going to multiply the 2 by 1/2. And 2 times 1/2 is 2 divided by 2, which is 1. And then I can take half of 1 and get 1/2. And half of a half is a quarter. 1/2 times 1/2. 1 times 1, 2 times 2 is 1/4. So we get 1/4. And it's getting, once again, closer to 0, but this time as we go to the right, that's why it has that decay experience. Now, you do want to plot points on the other side if you can fit them. And this might sound weird, but of course, when I said multiplying by 1/2 is the same thing as dividing by 2, well, if we multiply by 1/2 going to the right, then I guess we're dividing by 1/2 going to the left. But I don't think we like to say dividing by 1/2. So what can we say instead? Well, remember, we were just multiplying by 2, or we were dividing by 2 going this way. So you can imagine we're going to multiply by 2 going this way. Dividing by 1/2 is the same as multiplying by 2. We take half of it on one side, we double it on the other. And that's what we're going to do. So I'm going to go ahead and double 4 as I move x to 1 to the left here. Double 4 is 8, and I get 8 there. And if I double 8, I'm going to get 16. And if I double 16, I will get 32. Now, 32 does go out of reach, so I'm not going to plot that. But I am going to be drawing a curve that will still start from the top as best as I can here. Or not as best as I can, but as best as one effort will give. Looks like it's all just underneath. If I stay all underneath, I'll go ahead and shift it afterward. That's fine. And there we go. There's my drawing. And let's just do a little bit of a shift right here. It'll look nice. That's fine enough for me. There's my exponential function. And I'm going to draw the asymptote down below one more time. All of these graphs will not experience any sort of vertical shift or horizontal shift. So all of your asymptotes here will be on the x-axis. All of your a values will be their y-intercepts, things like that. So when my students hit integrated math 3, they'll probably be doing some of these shifts. And hopefully even without a table. It's pretty nice. Pretty quick graph to make without a table. I mean, I can go a lot faster, but I'm explaining things as I go. All right, give the domain and range. Now, domain and range last time here, again, was asking what are the x values, what are the y values. They don't change here. My domain here is, once again, all real numbers. I'm going to write it out this time. My domain is all real numbers. And actually, as long as we are not doing exponential models of growth and decay, you can assume all the domains will be all real numbers. There is no restriction for what I can plug in for x here. I will always get a y value out. That's really what's being asked. Generally, if you have an equation, your domain restrictions come in the form of maybe you can't take the square root of a negative, which is kind of weird because we're going to talk about imaginary numbers here. But I mean, on a real number graph, you can't take the square root of a negative and get a y value out as a point. Well, you could, but the x's aren't there. I should stop talking about that. Something where you couldn't divide by 0, for example. Maybe there's a domain restriction there. These don't have those problems. These don't have those problems. The range is the same thing. Once again, we stay above the x-axis. We never touch 0. We never touch negative. Y is once again greater than 0 on this range. So this looks very similar to the last one that we just did because it is. Now the end behavior of this one is going to be pretty close to similar, only there's a difference when x goes right versus when x goes left. It's kind of backwards this time. As x, I hope I used the word as last time. Good. As x approaches infinity, as we look forever to the right on this graph here, we got to recognize the notion here that y is now approaching 0. As x approaches positive infinity, y is approaching 0. As we go right, we're looking closer and closer to converging at 0. As x goes toward negative infinity, as we look further and further left on the graph, our y values will be found by looking up. Y is going to be approaching positive infinity in those cases there. You can put the positive sign if you'd like to. I'm not requiring it for my students. I have been putting it at times, though. All right. Is this exponential growth or decay? Now, here's the last thing that I wanted to mention on positive or negative exponential growth or decay, and here's just the ticker. If your a value, guys, is a positive number, you're going to have a positive exponential graph. If a is a negative number, you're going to have a negative exponential graph. And you're going to see some negative exponential graphs on C and D because a is negative there. So we'll see what those look like. Now, if b is greater than 1, you're going to be looking at exponential growth. Not just positive, it needs to be greater than 1. Multiplying by a number greater than 1 makes your value grow. And if b is between 0 and 1, like a fraction, like that, you're going to see exponential decay. You won't see b ever be 1, because multiplying by 1 wouldn't make anything grow. It would just keep it the same. And multiplying by 0 would just turn it into 0, which I guess keeps it the same. And negatives don't really work in these for b. b is always going to be a positive number, either between 0 and 1. This 1/2 gave us decay, and then this positive a here gave us a 4, what have you. B can be greater than 1 here. However, it is between 0 and 1, and it is positive. So guys, this is positive exponential decay. Every graph that goes in this direction here would be positive exponential decay. All right, here we go. Part C. Y equals -5 times 2 to the x power. All right. Now, you might have noticed, I just looked at this. I'm like, where's my bottom? You might have noticed here, I flipped this graph upside down. And if you look at any PDF thing that you want to print out, just go ahead and turn your paper upside down. I think that'll just be fine for you. So here, I'll make it upside down on one side for knowing that this is going to happen here. Upside down, remember, this is your y-intercept, and your y-intercept being 0, -5, of course, does mean that, we're going to start below the x-axis. And who's to say that we'll ever get above it again? As we see a growth factor there of 2, that means we will be multiplying our numbers by 2. Well, what happens when you multiply a negative number by 2? Well, it stays negative. And that's the point here. We aren't going to be looking at any positive numbers. You can tell why they call this thing a negative exponential function. So there's my y-intercept. My decay factor, my growth factor here is going to be 2. Which means I will double my values each time x increases by 1. Let's try and do this one a lot faster here. I'm going to start at 0, -5. Right there. And as I increase by x by 1, I'm going to double it. -5 times 2 is -10. So I'm at -10 there. And -10 times 2 is -20. And -20 times 2, far out of reach, is -40. I'll get those ones. Now I'm going to divide -5 by 2 going to the left. Okay. -5 divided by 2. Maybe use the mixed number version right here, -2.5. It's -2.5. So it'll be halfway. Look, it's halfway closer to the asymptote. If you're good at knowing this is 1, 2, 3, 4, 5, halfway is 1, 2.5. So -2.5 there. Now what's -2.5 divided by 2? This is where it might help when I said -5/2. That is, -5 divided by 2 is literally -5/2. And in dividing that thing by 2, you can say multiplied by 1/2. Right? Divided by 2 is multiplied by 1/2. That's -5/4. That's -1.25. So that'll be a little bit below -1 right there, a quarter of the way up. That's probably even a little too low right there if I'm to be really picky. Probably closer to, about right there or so. And just because I can fit another point or two, let's see what happens when we take -5/4. Notice how I'm using the improper fraction to do this. Here I get -5/8. And you might not know, I know what it is as a decimal. It's -0.625. But you might not know what it is as a decimal. Just know that that's more than 50%. It's more than half. So more than -1/2, just a little bit underneath it right there. That would be a good one. And at that point, I don't know if it's worth calculating the next one, but you would get times 1/2, which is -5/16. That's about a third. 5/15 is a third, so 5/16, it's about a third. But it's halfway closer to the asymptote there. I'm just plotting as many points as I can humanly fit, or that seem to make sense here. You do what you can. When my students do it, they'll be doing it on a computer, so I'll tell them exactly which points I want them to plot. They're not going to be doing more than one fraction/decimal, just for the sake of what I'm restricted and limited to doing with my platform that I use. So here comes the curve. It's going forever downward, and it's really, really increasing its pace there downward. So, we'll talk about that as growth versus decay there. Decay doesn't necessarily mean going down. Just keep that in mind. All right, so let's go ahead and look at the domain and range. Domain does not change, guys. This is once again going to be all real numbers. Every single x value in the book is hit. The range is different this case, though. We don't hit any positive numbers. We still don't hit 0, but now they're all negative, and we hit every negative in the book. And a way to say that we hit all the negative y values, we say y is less than 0. Y is less than 0. Okay. Now the end behavior of this one, chaps, as x goes toward positive infinity, as x goes forever right, now we're looking at y values that are down. right? So look to the right. If you want to find your points, look down. That's where they are. As x goes toward positive infinity, y is going toward negative infinity. It's going forever down low as we look forever right. As we look forever left here, what kinds of y values are we looking at? They're getting closer and closer to 0 right here. As we go forever left, they're going to keep converging toward that value. Now, this one here is not positive exponential something at all. This is, I'm sorry if you couldn't really see this 2 right here because my face is in the way. That's totally my bad. This growth factor here that I was writing, that's a 2 right there. Anyway, so this one's not positive at all, not because it's below the x-axis, but because it's below the asymptote, which is on the x-axis. This is a negative graph. As long as a is negative, like I said, you will be getting a negative exponential function. And this one, folks, this one is negative exponential growth. It's not decay. It's not decay. Despite the fact that as you're looking at this here, you may be thinking, well, it's going down. We're losing something. Well, sort of. I'm not going to get too deep into it, but you're growing negatively. You are growing negatively, and there's something to that. Negative doesn't always mean bad. It doesn't always mean you're losing something. It just means you're going a different direction. We are growing in the negative direction. Remember, b is greater than 1, so it is still growth. There it is. All right, and the last one, part D, as we spend a half hour doing just number 1 here, and we have 4 problems. Trust me, the other ones should be going faster, because this has a lot of bits to it. All right, negative 2 times 1/3 to the x power. Are we now used to recognizing a as the y-intercept that is 0, negative 2, where I can plot that thing right here to start. I already know where that's going to begin here. Let's get the scaling in. 5, I think 10, 15. I got to count this a little more this time. 15, 20, 25. All right, I start at negative 2. 1/3 is my decay factor. Yes, this thing will be exponential decay. Now, from the negative side, decay kind of means it's going up, but that's okay. The decay factor is 1/3. We will be multiplying by 1/3 each time. Not a pretty thing to do, but it has to be done. All right, negative 2 times 1/3. Negative 2 times 1/3. Well, that's negative 2/3. That's negative 2/3. So that's a little bit underneath, well, above negative 1 right here. It's 2/3 of the way toward there. So as x increases by 1, I get negative 2/3. When I multiply that number by 1/3, I get negative 2/9. I mean, it's close to it. It's a little bit underneath a quarter. It's between a quarter and a fifth. So, I mean, you know, you're taking 1/3 of this height right here. You only do the best you can. I don't think I'll be able to fit another point really beyond this one here. I'm just going to go ahead and just put it there. It would be negative 2/27. I couldn't even tell you what that decimal is. I know that's less than 0.1, negative 0.1, but it just gets closer and closer toward, of course, the asymptote. It shrinks. Hopefully you're okay with just that message of what's being talked about there. I want to get it a little approximate. That's fine. Okay, now going to the left side will be a little better for us as we divide by 1/3 each time. But dividing by 1/3 is the same as multiplying by 3. So I take negative 2 and I'm going to multiply it by 3 as I go to the left. We divided by 3 going to the right. Took 1/3 of it. Now we're going to triple it going to the left. Negative 2 times 3 is negative 6. Negative 6 times 3 is negative 18. So 5, 10, 15, 20. Here's 18 right here. And then that times 3 is negative 54. Can't fit it. We'll leave it. So my graph, that curve, is taken off. Well, it's technically not taken off. Remember, we should be saying as x goes further right, but takes off as x goes left. And my asymptote, of course, this dotted line, just kind of saying, you shall not pass. Sounds good. All right. Domain. Have we learned that the domain for these ones is all real numbers? I sure hope so. Here comes our domain. All real numbers. Let's bring the symbol back. The range only points underneath the x-axis here. Y is less than 0. Every y value hits less than 0. There we are. Here comes the end behavior, guys. As x goes forever right, we are getting y values converging toward 0 once again. Look at that graph and say, as we go right, that's where we're going to see our y values get closer and closer to, converging toward 0. And as x goes left toward negative infinity, your points you're going to find are down underneath the x-axis, going further, closer and closer to negative infinity right there. Left and down is where we find our points there. There's the end behavior. And guys, this is negative as it is underneath the asymptote there. It's negative, and this is exponential decay. Now, in decay, what happens is as x goes further right, as time goes on, you converge closer to the asymptote. So it's shrinking from the negative direction. That's a way you can say decay. Even though it's going up, it is shrinking from the negative direction. Okay. All right, I think I'm done with that number 1 here. It did take a half hour to take all those on, so I hope you learned something doing that. All right, number 2. I think numbers 2 and 3 are both word problems with exponential growth or decay models. So let's go ahead and take a look at these. I got to fire up my graphing calculator here as well. I'm going to get that started while I'm reading this problem here. So get your calculator handy as well. And I'm going to speak I'll see as briskly as I can talk about the stuff when it comes to rounding. I hope it'll make sense. All right, Audrey buys a widget that is expected to appreciate by 6.5% every year for $157,000. This is how much she bought the widget for. I know the sentence is kind of weird. She buys a widget for $157,000. She expects it to appreciate. That doesn't mean that it's going to appreciate her. That means it's going to rise in value. She expects it to rise in value. Give the function that models this situation. What will be the value of the widget in 17 years? What is the domain and range? Describe the end behavior. I don't see a place where it shows end behavior here. I did not create this. But here's what we have to do. There's a formula involved here, and there are different letters used based on the book that you see, the teacher that you have, the website that you're on, anything like that. But they all come down to the same bits here. The formula looks like this, and it's not unlike y equals ab to the x power. Y equals ab to the x power. Y is still y, a is still a. Instead of b, I have this 1 plus r or 1 minus r, depending on whether we're doing an exponential growth or decay. And then x is replaced by t, because we're going to be referring to time. And time is just as time goes on, it's a number of years that something occurs. We're going to be using that. So we need to, we're going to keep t as the independent variable. We're going to write it as t for the model until we substitute 17 when we find this part out here. Save t for now, keep the variable t. But we do need to insert in a, and we do need to insert in r. Now, a is a factor of, not literally factor, a is a component of what we saw before was the y-intercept. A y-intercept, guys, is kind of like a starting value. When x equals 0, y equals blah, 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 right? When x equals 0, y equals -2. So here, when t equals 0, that's time 0. That's 0 years. Not like year 0 AD 0 years, but 0 years since you've started doing whatever it is you're doing. And in this case, we have Audrey who bought a widget at year 0. And then the clock starts ticking for her holding on to that widget and it appreciating in value. So at year 0 is when she buys it. A is the initial value. It's the initial value or the initial population. It's the initial whatever it is you're referring to here. For us, it's 157,000. When I start writing my equation, guys, A is $157,000. Now, R is a part of your growth or decay factor here, and R has to do with this percentage. When you appreciate by 6.5%, it means it's increasing by 6.5%. Currently, it's at $157,000. That's 100% of how much it's worth. That's what the 1 has to do with. What we're going to do is convert percentages to decimal, and 100% converted as a decimal is just the number 1. That's what this number is doing here. We take 100% of the value that we have, and we are going to add another percent on top of it. We're going to add 6.5%. Now, 6.5% as a decimal, there's a decimal in here, but the decimal equivalent, see, percentages are 100 times larger than the value that they actually are. I got to shift this 2 decimal places over here, and then I get 0.065. So that becomes 0.065. So what I'm going to do for this function here, I'm going to substitute, that's r, by the way. I'm going to substitute 0.065 for r. I'm going to substitute 157,000 for a. I'm going to simplify what's here, and I'm going to use the plus because I am increasing. The appreciation says we're increasing. So this equation is going to say y equals 157,000 times 1 plus 0.065, all raised to the t power. And if I simplify this inside, which I'd like to do, that's now going to say y equals 157,000 times 1.065 to the t power. That is the model for this thing that projects how much this thing will be worth after t years, because t equals 0 is when she bought it, and then t equals 10 would be 10 years later and things like that. And 17 years later is something we'll be solving for. Hopefully this is starting to look a little bit more like a y equals ab to the x, even though the numbers are weirder and we're using a t. Now, the domain for these word problems is a little bit different from before. Remember, Audrey did not own this widget before she purchased it. I don't need a D again. Audrey did not own this widget before she purchased it. Years before t equals 0 do not qualify as far as this thing appreciating. We don't know when this thing might have been made the second before she bought it. This thing might not have been able to increase in value until somebody owned it. We have to assume here that our domain occurs and starts when she buys it. So we can't look at years before she bought it. We have to look at when she buys it, which is at year 0, and then every year afterward. Your domain, it's not x anymore, it's the letter t. Your domain is t is greater than or equal to 0. These are the points that we're going to look at. So although exponential functions should have an all real number domain, when it comes to context of a problem, the model that we're using might not necessarily use it in the same fashion. The range is a little different here as well. See, if we had this graph here, and I'm not going to get really detailed on the graph, but if we have this graph, this is a positive exponential growth. It's doing something like this. But here's the thing. We start at year 0. Anything before that's getting closer to the asymptote and such is completely ignored. We got to erase it. We're only looking at first quadrant stuff. We start on the y-intercept, which is $157,000, and the money only goes up from there because it's growth as this appreciates. This isn't just any positive number. We never look at numbers that are less than $157,000 based on this model. We are only looking at numbers that are $157,000 and greater. 157,000. We don't just say y is greater than 0 in this case. That's where it kind of begins. And that little mini feature of a graph kind of shows you that. Now, the widget's value in 17 years means we have to substitute 17 for t, and then we got to figure out, how much it's going to be worth at that time. So what I'm going to do is we got to solve for y, once again, when we substitute 17 for t. And I won't explain why right now here, but when you go to the calculator, please just type this in exactly as it's written. Don't use multiple steps for it. The reasons have to do with order of operations and rounding early. Things like that. In fact, we'll talk about rounding. We're actually kind of not going to round at all in some ways. You'll see what I mean. But when I go to my graphing calculator here, I am going to do 157,000 times 1.065, and I'm going to raise that to the 17th power. And I'm getting a number. I'm going to go ahead and write it down on my screen, and then I'm going to fade away from the calculator here. I got 4. That's good. That's good money. 457,976. It was 17 years. That's more than half my life, though. 2794. 2794. All right. Let's look at the number that I wrote here. 457,976.2794. Now, this is a word problem, and in a word problem, there's probably context such as units of measurement. What we are talking about here are dollar amounts. It was 157,000, and 17 years later, it's this many dollars. So what I'm going to write here, I know I wrote some of the work there. I'm just going to write it here and box it. This is a dollar amount, 457,976. And can we have a decimal for dollars? The answer is yes. You can have 2 decimal places regarding your cents, and you should put them. So I'm going to go ahead and put and 27 cents right here, and that would be my answer. Now, a lot of people who think that they are above me right now for this math question are going to shout out loud and say, wait a second, hold on, there's a 9 after the 7, and I know if that number is 5 or more, you're supposed to be rounding up. Well, here's the thing. And this is argumentative depending on who you talk to. You can find websites and ask teachers depending on what they want you to know. I have not reached my 28th cent yet. In the context of this problem, once the exactly year 17 hits, however much a cent matters to you and however close I am to that cent, I have not yet reached it. The way that I told my students with this is, let's say that you can jump and have a reach of I didn't say this exact number, but let's say at 9.99999 feet in the air, I can't touch a 10-foot basketball rim. I'm so close. Maybe a hair follicle is just brisking it. I can't really feel it, whatever it is. But I can't touch a basketball rim. You can't just round it up and assume that. I didn't yet hit that ceiling of whatever that is. Not until I hit that number does that number register. So instead of rounding for these word problems, which would be an approximation either way. How much does the cent matter? I don't know. But and maybe 2 seconds later it'll actually hit. But as far as that goes, guys, I truncate it. I get rid of it. 2 decimal places. That's my answer. That's how I'm asking my students to do it, and they'll lose just a tiny hair of credit, partial credit there, for rounding incorrectly, because we're not rounding here. All right, that is number 2. Number 3 is another question of the same vein, only now we're going to look at depreciation and, of course, different numbers. Number 3, Bryce buys a... what? Oh, a thingamajig. Bryce buys a thingamajig that is expected to depreciate by 3.2% every year for $15,500. Once again, he bought this for $15,500. I didn't write these sentences, but that's how much he bought it for. It's expected to depreciate. Why would I buy something that's going to devalue over time? Literally everything does that. I mean, intrinsic value, like a car. Well, most cars go down in value too. Anyway, he's probably not intending on selling it. Who knows? All right, give the function that models the situation. What will be the value of the thingamajig in 9 years? What is the domain? Oh, describe the end behavior. I'm sorry, I have to go back to number 2 really quickly. This is the problem when they don't ask me to actually fill that out. My students might forget to fill it out as well. But describe the end behavior, just to speak on this really quickly here, guys. I don't know why they're going to ask me this here, because x can't approach negative infinity, so I can't really speak toward that. Let's just say just what's happening just as x goes forever to the right. So as x approaches positive infinity, because there is no end for the other side, we start at one time and there we go. As x approaches positive infinity, y approaches positive infinity. I'm sorry guys, that's your end behavior bit. My bad. I'll try to remember that for the other one. All right, here we go. Number 3, one more time. This model that we're referring to, the equation is y equals a times 1 plus or minus r to the t power. We will add r if we're talking about something increasing, we'll like a growth. We will subtract r if we are referring to a decay. This one happens to be a decay. This one is depreciating over time. We're losing value. It's not becoming 3.2% of what it was. It's losing 3.2% of what it was. Basically, whatever it is at 100%, now it's the next year it's about 97% of what it was. Take away 3.2. But let's go ahead and convert those the way that we did last time here. Your A value is 15,500. It's the initial value you have there. The R value, remember 3.2%, we got to shift this decimal 2 places to the left. 3.2%, shift it 2 decimal places, and it becomes 0.032%, 0.032%, not percent, just 0.032. So R is 0.032. You know, again, I didn't write these. I really would have liked to see one that was just 32%. Guys, just a heads up so you know, because we're not going to cover it, looks like. 32% is 0.32. There is no 0 in between a tens place value right here, but 3.2% there is an extra 0 there, so you know. All right, guys, we are going to substitute these numbers in, and I will be using minus in the equation as it's a depreciation. So we'll see y equals 15,500 times 1 minus 0.032, all raised to the t power, which becomes y equals 15,500 times 0.968. I'm doing that in my head. 0.968 to the, I'm not bragging, I'm saying, I apologize if I'm wrong. 0.968 to the t power there. You can use a calculator to get that one. The reason I said that is because 100 minus 3 is 97%. Take away another 0.2, that's 96.8. I think that's right. So listen, guys, we're going to multiply by a number that's between 0 and 1. That makes this thing decay. These numbers will go down over time. If we look at the appearance of what this graph would have been, disregarding the domain restrictions we're going to have in a second, this graph is going to do something that starts somewhere and it's going lower and closer to the asymptote like that. We're going to be starting at year 0 here, of course, so we are going to be erasing everything that comes before it. And at year 0, it has an initial value of $15,500. But it's getting closer and closer to the asymptote, which is on the x-axis, or the t-axis right here. And yeah, it's just going to keep shrinking. Why was I bringing this up? Oh, because it's decay. When I multiply by 0.968 each time, it's shrinking and getting closer over time. That's a good talk on end behavior as well when we get to that part. But let's do domain and range. Domain, once again, for the context of this word problem, is t is greater than or equal to 0. Once he buys the thingamajig, the value starts going down in that way. We can't anticipate that it was doing that beforehand. Let's pretend it was a car. The thingamajig is a car. That car on the lot, may lose some value over time, of course, because they get new models in. But once you drive it off the lot, guys, is now when it's used, and that's when the value really starts to go down. Probably more than this. Some car. All right, the range here is a different story compared to last time. Last time the range started at 100 $57,000, and then it skyrocketed toward infinity. This time, it starts at $15,500 and it shrinks over time. But there's a certain number that it never quite hits because the way that these things function here never truly hits like zero, or it's never going to be negative. That would be weird if you get negative dollar value for the stuff, as in you sell it and you pay someone money for it. So the range here, guys, the Y value has to be greater than zero, but it also needs to be less than or equal to the 15,500. So it needs to be less than or equal to this, but it also has to be greater than zero because the nature of the asymptote. So the range goes in between those two. This is the highest it'll ever be for Bryce, and it'll stay above zero. I guess he could always sell it for a cent, depending on how you, well, I don't want to say the word round, but depending on how you truncate off your decimal, if it was after 100 years, I don't know. All right, what's its value in 9 years, though? Let's go ahead and substitute 9 for t in this original equation that we had up top here. We have y equals 15,500 times 0.968 to the 9th power. And of course, calculator time. We are not doing that without a calculator. Heck no. So calculator time, let's go to the calc. And I'm going to do 15,500 times 0.968 raised to the 9th power. Let it do its work for you, and we're getting that number there. Let me write it first. Y equals 11566.71178. Okay. This is another dollar amount, and before we kind of move forward, again, I didn't create these problems, so I did want to state that if this was a population question where you lost 3.2% of people every year in your population, please note that although dollars can have 2 decimal places, population is in terms of number of people, and we can't have decimal number of people. So based on the context of the situation, if this was about people, we would, only be looking at a whole number like that. We wouldn't be also looking at the decimals. However, because this is dollars, we are looking at y equals, forget the y equals. We're looking at a total dollar amount here of $11566.71 or $11,566.71. Now, the decimal argument as far as rounding, the rounding not rounding thing goes, what I tell my students is in decay, it's a little bit harder to consider whether or not you are touching that floor. I'm not speaking because they're not talking about fish population and dying, the fish dying or something like that, so I can't explain it in full here, but I allow them to also use the other number right here, which is 72 cents. They can use one or the other in a decay model because this one, and I've looked online, I've tried to find out, and I've asked other teachers, they generally just say round. I don't care either way here. The growth one I have a stronger conviction for, where I state that make sure you don't round up because you haven't yet reached that number. But the question is, did I fully actually lose this cent yet? I would say you did. But in other situations, I can understand why you say that you didn't fully lose it until you get back to the other thing. So I don't know. I would say you did lose the cent, but either would be accepted on my end. Often I just say truncate though. Just get rid of it. Move on. All right, the end behavior for this one this time, remember, I'm not going to look to the left because at the left is just, we start at that number. It's not a behavior, it's an actual value. But the end behavior of this thing as x goes toward, or did I say x last time? This is a t, guys. That's my bad. This is a t. As time goes on, as we go toward infinity years here, your y value is getting closer and closer to 0. We are getting this thing, if Bryce held on to this and was immortal or passes down generation to generation, and it truly depreciated by this each year, at some point it's going to reach a cent, 1 cent. These are models, so I don't know if it actually does that, but eventually you give it away for free. So it's getting closer to 0. It never increases in value. There it is. And there are some things that lessen value, and then over time, boom, they expand in value. All right, let's move forward. Number 4, we have, we're done with the exponential stuff with models and graphs and stuff. Now we're going to start looking at quadratic equations, and then we're going to go back to exponential expressions, something that I did earlier with my classes several weeks ago. And then we have some more on imaginaries. Probably not all in the best order, these problems. All right, solve each by taking the square root of each side. Simplify all radicals, rationalize all denominators, give exact answers, no decimal approximations. I love the instructions for that. I am not going to enforce in any of these problems. You're going to see future problems here where they'll say solve by completing the square and quadratic formula. I'm not going to enforce a specific way for you to do this as long as it's by hand and algebraic. However, these ones, you'd be hard-pressed to not solve using square roots. We have one x term there, and it's an x squared, and we can isolate it each time. It's already isolated as a term right now on part A, so as I start this thing, I can divide both sides by 4, and now my x squared is completely by itself. X squared equals 32 divided by 4 is 8. To solve for x, I need to take the square root of both sides here. The square root of x squared, in our case, becomes x. And on the right side here, I'm going to be taking plus or minus the square root of 8. Now, the square root of 8 can simplify. We can turn that into, this is where I'm going to go kind of fast now as far as things that I expect students to know as long as I can show the work on it. So the square root of 8 turns into the square root of 4 times square root of 2. If you're asking why that is, then I do, I mean, if you're not one of my students, then I guess I'd understand, but think about it, 4 times 2 is 8. With square roots, properties do align that way. You're allowed to do that. Now, why did I choose to do this? Because I can take the square root of 4. When I simplify a radical right here, the square root of 4 is 2. The square root of 2 stays as the square root of 2, guys. I can't do anything with that. So I'm going to leave it like this. I'm going to leave it like this right here, and that's what x equals. There are two answers to this thing, positive 2 root 2 and negative 2 root 2. Because when I square even a negative, that turns positive anyway. It turns into 8. And then I multiply by 4 and I get 32. There's the answer. You can see that these will go a little bit faster, I sure hope. But this is where if I go too fast, people will ask questions. So we'll see if there's something I need to slow down on here. All right, part B. I'm going to divide both sides by 10 here as the x squared term is already isolated. And I'm left with x squared on the left side here. And on the right side, this 16 over 10, you know, I can reduce this thing. I can reduce this thing to 8 over 5, and that I will do. So x squared equals 8 over 5, and now I must take the square root of both sides here. Now, just like a product, well, listen, the square root of 8 here, I'll write this. The square root of 8 is the square root of 4 times 2, which splits to the square root of 4 times square root of 2. As a product can split up this radical here, a quotient, a fraction, can also do the same thing. What I mean by that, y'all, is that right here, x equals plus or minus, I'm going to be taking the square root of 8, and I'm going to be taking the square root of 5. Now, neither is necessarily, you know, they're not perfect squares, and we have to rationalize all denominators and simplify all radicals. So we have several things to do here, and there's an order. You can choose which order you want to do these. Right now, since I have no perfect squares, I'll just kind of, you know what? Let's just simplify the top first. The square root of 8, is 2 root 2. We just saw this here before, so I get 2 root 2 on top, and on bottom I have that square root of 5, okay? Now, here's what we have to do in rationalizing a denominator. The square root of 5 is an irrational value. It's an irrational value. We must make it a rational number. Basically, let's try and make it a whole number. And in making it a whole number, just like what we do to find a common denominator and such, we got to multiply top and bottom by the same number as to not change this value, but to change the appearance of what we see on bottom. So I am going to multiply the top and bottom here by the square root of 5. And the reason I choose the square root of 5 is because the square root of 5 times the square root of 5 equals 5. If the square root of 5 asks what number times itself, what's the number that when I multiply it by itself gives you 5? Well, that's that number that I'm multiplying by itself. And that does give you 5. So this on bottom is going to say 5. On top, I have 2 times the square root of 2 times the square root of 5. And just like you can take any one of these guys and merge them together inside a square root, you know, or just like we can split it, we can also merge them back. So I can take the square root of 2 times the square root of 5 and give myself the square root of 10. So that'll turn into 2 root 10 over 5. Now, a couple things to this. Number one, when we simplify an expression, when we simplify this thing here with a radical involved, as you saw, I got to rationalize the denominator, but also I should only end up with one radical in the end in my answer. Per term, I should only have one radical. So I shouldn't have had 2 root 5. It does become root 10. Number two, if root 10 could simplify as a radical, I would continue to do that. And that's where I was trying to think, did I want to take this right now and rationalize and do root 5 over root 5 to show you that when I get root 40 on top, I got to simplify that further to get to 2 root 10? I could have shown that, but root 40 does get you to 2 root 10 just as well, just so you're aware. But check to see if you got to simplify that. It appears that we can't because there are no perfect squares that exist in a 10. Factors, I should say. Number 3. Try and reduce the fraction if you can in the end, this 2 over 5. I can't, but number 3b with this is not 10 over 5. I can't reduce this 10 over 5 and turn it into 2 over 1 here because this is not a 10. This is the square root of 10. So make sure you're careful with that. If this was still a square root of 5, I guess I could divide them, but then I guess I still have some rationalizing to do or something. I would have probably done that early on with this. Well, look, I did do it early on. 16/10 turned into 8/5. So I did do that early on when I worked on the problem there. So yeah, there are a lot of ways to do this problem. This was just one way. I did the fraction reduction first. I did the simplification of the top second. I did the rationalization third. You could have left this unreduced. You could have rationalized first if you wanted to. Then you could have simplified and then reduced the fraction. You'd still get to the same answer, which does not have a root 5 in it, by the way. There it is. Okay, part C. X squared plus 20 equals 0. Now, as you saw in these previous problems, it makes sense to get x squared on its own side of the equation, so then I can take the square root of both sides. So I'm going to begin by subtracting 20 from both sides here, and I'll be left with x squared equals negative 20. So I'm going to take the square root of both sides. Now, last semester with my class, if we were taking the square root here, we would stop and we would say there's no real solution. It's correct, there is no real solution, but we didn't yet know the imaginary solution set, the complex numbers that we can get here. There's a way of taking a square root of a negative that uses the component of this form of this letter I. And this is something, unfortunately, time-wise, guys, I'm almost at an hour. I'm not going to get into why this is what it is or what the relevance of it is. I will give you the process, though. I hope that's okay. And it's going to look like this. When you take the square root of a negative, you can rewrite it as the square root of a positive as long as you pull an I outside of that square root. So square root of negative 20 becomes I root 20. The plus or minus comes as a result of taking the square root of x squared. This plus or minus wasn't absent anytime we did this. This has nothing to do with the I thing. The I has to do with the negative inside the square root. You can tell the square root's not positive. So there's an I here. And I'm not saying I is a variable, but everything we do with I, we will treat it like a variable when it comes to combining like terms and such, with the exception of when we hit what's called I squared. And we'll get to that when we get there. Okay, so x equals plus or minus I root 20. Now, you would be done if you couldn't take the square root of 20. And 20 is not a perfect square, but it does have perfect square factors. You can divide a 4 out of 20, right? So here, the square root of 20, I can rewrite that as the root 20 is root 4 times root 5, which would then become 2 root 5. So x equals plus or minus, I got an I multiplying by 2, and I'm going to rewrite this in a second here. 2 times the square root of 5. Once again, the square root of 4 is 2. The square root of 5 stays as the square root of 5. This I times 2 is a little weird. This is one of those times where you might treat I like a variable, in that kind of make 2 the coefficient and make I go afterward. So I'm going to write 2I root 5 like that. And that would be a final simplified answer to that thing right there, to that puppy. And I know those can get a little weird when it comes to the I, but let me tell you this. The only difference between the answer to the question with x squared plus 20 equals 0 and x squared minus 20 equals 0 is here when we say x squared is 20 and we take the square root, here we would get x equals plus or minus 2 root 5. What's the difference between these two answers here? Literally just that letter I. I mean, it's a big difference. This makes these the imaginary number set. And let me clarify right now, imaginary numbers don't mean that they're made up. They're every bit as real numbers. They just don't exist on a real number plane. There's a whole new plane that's used from it. But the point is, the answer here, don't let too much stuff confuse you with regard to I. I is just an extra letter that's added. So if you need that negative to kind of get out of the way for now and just insert the I at the end of the problem, go ahead and do that. That's totally your call. But yes, there's no real difference between those two answers there. So hopefully it doesn't get too confusing with an I. You're literally just throwing in a letter. All right, part D. Part D. 5x squared equals negative 7. Oh, I see where this is going. Divide both sides by 5 here. And now we're going to be getting x squared equals negative 7/5. And now I must take the square root of both sides. Not necessarily a fun problem because we're going to have to do several things here. We have an I involved, okay? We also will have something else. You'll see it. All right, here we go. Oh, I was going to say we also have to rationalize the denominator. All right, x equals plus or minus. Let me just start with this step here. I'm going to start by writing I root 7/5. Now, I do need to split up this fraction here, the square root of the fraction into a fraction of 2 square roots. So this becomes x equals plus or minus I. I'm going to put the I on top. You know, clearly I is like a numerator value right now. So I'm going to multiply it up there with the 7. The root 5 is just going to be on its own. Hopefully you recognize that, guys. I is multiplying, and of course it's a numerator value. So I'm putting it up with the numerator. Square root of 7 or square root of 5 are not only not perfect squares, but they cannot simplify. However, the square root of 5 does need to be rationalized because it's in the denominator. So I'm going to multiply top and bottom by root 5, the number that would help give me just a 5 on the bottom. And that's exactly what that thing is going to do. So let me write it down here. This will say x equals plus or minus I. Root 7 times root 5 is root 35, and this is all divided by 5 right there. And that is the final answer to that one. So the square root of 35 doesn't have a perfect square factor in it. It is not a perfect square in and of itself. I'm going to leave it like that. Two different answers, positive I root 35 over 5 and negative I root 35 over 5. No decimal approximation, guys. No calculator usage. These are exact answers, as exact as you can get. And there are two solutions to all those. I hate when this thing bugs out like that. All right, letter E. Let's go forward. 3x squared plus 8 equals 0. Solve for x. Let's start by subtracting 8 from both sides there. And I'm going to get, with some room to spare, I'm sorry that this looked a little cluttered, but I'm glad I color-coded it. 3x squared equals negative 8. And I shall now divide both sides by 3. And I will get x squared equals negative 8 thirds. Not done. I have to solve for x, not x squared. So I will now take the square root of both sides. And if you can imagine, this is a lot like the last problem as far as negative 7/5. I'm going to skip this step here, and I'm going to go straight into this one where I have I root 8 on top and root 3 on bottom. I hope you're okay with that. That would look like over here. Whoops, the wrong blue. That would look here like x equals plus or minus. I'm going to have I root 8 on top. I'm going to have root 3 on bottom. Okay. Now, not done in several ways here. If you remember last time where I said I simplified the square root of 8 before I rationalized, this time let's rationalize before simplifying the square root of 8, just to mix it up and show you kind of what can happen when we do this. In rationalizing, I'm going to multiply the top and bottom by the square root of 3. And just so you understand the reason why we got to multiply top and bottom by the same number, I stated before, you cannot change the value of what you have here. And root 3 over root 3 is 1. Multiplying a number by 1 doesn't change its value. We established as such when we talked about exponential functions. That's why b can't be 1, because the value wouldn't change. All right, so in multiplying this stuff here, I'm going to have x equals plus or minus. Now, on the bottom, there's just a 3. Root 3 times root 3 is 3. On top, I have a root 8 times a root 3, and that's root 24. So I have I root 24. Now, we would be done in this case. However, in this case, because I did not simplify this radical earlier, this radical still remains unsimplified. I can simplify the square root of 24 because there is a 4. We're looking at a lot of things with a 4 in it. 4 is a perfect square. 9 is a perfect square. 16 is a perfect square. 25 is a perfect square. We're looking for these numbers here that we can take the square roots of when we're simplifying radicals. And that's that goal there. This list goes on forever. It seems like there are a lot of 4s involved. Again, I don't know if I wish that I made this assignment. That would take way too long for me to do, given my limited time. But I'm choosing a number here that I can pull out of this here because I can take its square root. So the square root of 4 is 2, so this becomes 2i root 6 on top. This will become 2i root 6 on top. So this will now say x equals plus or minus 2i root 6, and this is all over 3. Now, 2/3, again, this is not a 6, it's a square root of 6 here, so these cannot divide, and 2/3 cannot reduce anymore either. So that would be the end result. That's 2i root 6, all divided by 3. Some pretty good practice solving using square roots there. I think the next sets of problems that we do, we solve using completing the square or quadratic formula, and I'll make sure to mix and match here. Okay? Yeah, so for number 5, it says solve by completing the square. I'm just going to say solve each algebraically. There are some where I am going to actively choose against completing the square because I don't want to do any where I have an A that's not like this one here. Well, I could do it here. I might do it here. I don't want to do it here. I don't want to do it here. There are reasons. I'm going to use quadratic formula. I'm assuming these are not factorable. When we're working on these, I'm assuming a lot of these have imaginary solutions, and we're going to practice that way, but we'll see. Simplify all radicals, rationalize all denominators, give exact answers, no decimal approximations. This time we cannot solve using square roots unless you do the completing the square, because then you could factor it into a squared quantity. So we're either going to use quadratic formula or completing the square. The first one I'm going to use completing the square. It's very already set up that way. Completing the square means that we take the quadratic and linear term of a quadratic equation. We're going to create a trinomial out of this that makes a perfect square trinomial, something that factors down into something squared. This allows us to take the square root of both sides. Now, I have a negative 21 on the right side, and whatever I add to this left side of the equation, I have to add to the right side of the equation. Now, there's a specific number that we're going to use. As long as this is a 1x squared right here, I can take this linear term, or the coefficient, the negative 4, I can divide it by 2, and that becomes negative 2. And then I'm going to square that thing, square it, and I get a positive 4. It will always become positive by squaring these things here, as they're not imaginary numbers, and squaring doesn't lead to negatives. So I add a 4 here. That means I'm also going to be adding a 4 right there. All right. Now, x squared minus 4x plus 4 factors down to x minus 2 quantity squared. The little shortcut trick here is that this negative 2 that you found from dividing by 2 is the same number that goes into there. But the two numbers that multiply to make 4 and add to make negative 4 are negative 2 and negative 2. But you do want to write this as this form here, so then we can take the square root of both sides, which is that next target. So x minus 2 quantity squared equals negative 17. Now to get x by itself here, I do want to take the square root of both sides, like so. Take the square root of both sides right there. And then we will be getting x minus 2 on the left side. On the right side, I have plus or minus, and this is I root 17. Once again, take the negative out of the square root, turn it into an I. This is now an imaginary number here. And to get x by itself, I'm going to add 2 to both sides. I'm going to write the 2 out in front of here. I have 2 plus or minus I root 17. This is a complex number solution. There are 2 answers to this. There's 2 plus I root 17, and there's 2 minus I root 17. These are known as complex numbers. All of these are, every number you've ever seen is a complex number. But when you have the real number term portion and the imaginary number term portion, that is a complex number thing in the form a plus bi. That's all I'm going to say. It's called a complex solution pair. All right, part B. I would have solved by completing the square if this 5 was not an odd number. I don't want to divide it by 2 and get a decimal or a fraction and work from there. That's not to say this won't have a fraction answer. I'm certain that it will, but the quadratic formula by nature is already all divided by something. There's no cause or concern when it comes to getting a common denominator or something like that. Now, there may be some other struggles along the way, but I'm going to work with it. I'm going to use quadratic formula. So to use the quadratic formula, I need to add 20 to both sides because I need to set this thing here equal to 0. So when I add 20 over here equals 0, we are looking at an a value of 1. That's the quadratic coefficient. We're looking at a b value of negative 5, and we're looking at a c value of 20. Okay. Now, the quadratic formula is the following. It's x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, with this quadratic formula, I like to first dig into what's called the discriminant, which is just the b squared minus 4ac. I like to anticipate how many real solutions we're going to have. I like to save room and energy in doing all the writing here. So I'm just going to first work on that discriminant of b squared minus 4ac. I know there's very little room here, but b is negative 5 minus 4 times a times c. I know where this is going. We got 25 minus 100, which is negative 75. So there are no real solutions to this thing, but we're still going to continue and solve with I. There will be 2 complex solutions to this thing. This is the thing that goes inside the square root. And if it helps, let's go ahead and clean this part up as well. What's the square root of negative 75? Because that's the thing that goes inside the discriminant. Well, that is going to be I root 75. And 75 is 25 times 3. Now, why did I choose 25? Because I can take the square root of 25. The square root of 25 is 5. I times 5 is 5i. So that's 5i root 3. This whole square root of b squared minus 4ac turns into 5i root 3. Now this problem is no different than any other problem if it was just x squared equals this, and this is how we'd solve here. Now you might have noticed I didn't put a plus or minus. The quadratic formula will already have the plus or minus, but notice we only do the plus or minus when it comes to solving for a variable. Right now we were just evaluating a discriminant, no plus or minus yet, but as we start solving for the variable, the formula will show a plus or minus. So let's go to work on this thing, guys. Let's look at the formula here. This will say x equals negative b, which is the opposite of negative 5, plus or minus. This is the 5i root 3 is that square root of b squared minus 4ac. So 5i root 3, all divided by 2 times a, 2 times 1. Let's get rid of the formula. I think that most people who are this far probably know it, or they have access to it somewhere, or they can rewind now that I've used the formula here. So let's go ahead and clean this thing up a little bit. Actually, not much. All we got to do, the opposite of negative 5 is a positive 5. Hang on, I want this to say x equals positive 5 plus or minus 5i root 3 I, all divided by 2. And that's it. We're done. Now, there are different kinds of problems where fractions might have to end up being reduced, and I can imagine it'll show up in one or two ways every so often when we do these. Case in point, if this was a 20 instead of a 2, then this 5 could divide by 5, this 5 could divide by 5, and this 20 could divide by 5, and I'd be left with a 1, and a 4. So you could do something like that because all these numbers as separated terms here all have a common factor of 5 involved. However, this was a 2. Therefore, I'm just going to leave it there as a 2. I can't divide 2 by 5 and get the same thing. There's my fraction answer that I anticipated. I said we'd be getting something like that. Okay, part C. I will solve by completing the square. I'm going to do it as often as I'm able to. Now, you cannot solve by completing the square unless you're looking at a positive 1x squared. All of these are negative terms right now. Even if I did quadratic formula, honestly, I would make all these positive. So you can either add all three of these things over, or you can multiply everything by negative 1, or divide everything by negative. However you want to put it, we're going to switch all the signs. 0 times negative 1 is still 0, so we're going to get an equation now that says x squared plus 6x plus 11 equals 0. And if I subtract 11 from both sides here, because I'm going to solve by completing the square, this constant term doesn't help me complete the square. I need another number to make that perfect square trinomial. I'm going to be getting an equation that will then say x squared plus 6x equals negative 11. Now I'm leaving some room because I'd want to complete the square right here. I'm going to add a number that goes inside there. Sorry, one sec. I'm going to add a number that goes inside here, and I will add that same number over here. The number I get is by taking this 6 and dividing it by 2. 6 divided by 2 is 3. And I go ahead and I square that 3, and I get 9. So the 9 is the value that goes in here that makes a perfect square trinomial that is factorable that we can play with. And here I have negative 11 plus 9. Like, as always, I see where this is going. We'll have imaginary solutions, or complex solutions, I should say. X squared plus 6x plus 9, that factors down to x plus 3 quantity squared. Once again, it is the two numbers that multiply to make 9 and add to make 6, or when you divided the 6 by 2. That's the number that goes there. And then negative 11 plus 9 is negative 2. So x plus 3 quantity squared equals negative 2. All right. I am going to take the square root of both sides here. And as we're taking the square root of a negative, you know that an I will appear. So here I have x plus 3. And on the right side, I will have plus or minus. This will be I root 2. The square root of 2 is not a perfect square. There are no perfect square factors. We'll leave it as square root of 2. I just got to subtract 3 over now, and that'll become x equals negative 3 plus or minus I root 2. And there are the two complex solutions that you see there. For my students, this is old rehash that they're like, oh yeah. And remember, once again, honestly, the only difference between these things is instead of taking the square root of a positive, you're now taking the square root of a negative, and now there's an I. Nothing else has changed. Zilch. Nothing else has changed here. Just when you take the square root of a negative, you introduce an I. Now, these aren't graphable. What I will mention is, if you have complex solutions such as these ones here, what it's saying is this quadratic, this parabola, does not cross the x-axis at all. The imaginary solutions do not exist on the xy coordinate axes number plane thing the way that other ones would if you had real solutions. Did we have any real solutions here? Not yet. Not yet. I don't know if we're going to. I'm going to imagine none of these are factorable. I can tell when I'm looking at a lot of these that they're not. But I also don't know if all of these are imaginary. I can probably assume that they are. That's what we're practicing right now. So get used to one way or the other. All right, I definitely want to use quadratic formula on this one where a is 2, b is 3, and c is 7. Not only can I not turn a into 1 without leaving fractions here, because I need a 1x squared to complete the square, but this is already an odd number, and then it's going to create a fraction when I turn this into a 1. Basically, this is quadratic formula bound. This is why I'm not going to use completing the square for all of these here. I want to use a different color, though. Whoa, hello, I want my problems back. Thank you, very nice. All right, let's go ahead and change this to that kind of maroonish color here. X equals negative b. Oh, hang on, discriminant first, right? Safety first. Let's go ahead and get that discriminant done by doing the b squared minus 4ac. B squared minus 4ac. I know where this is going. Equals 9 minus 8 times 7 is 56 equals negative 49. Hey, oh, sorry, no, it's not. It's negative 47. Shoot. I was going to say negative 49 is not bad. It's negative 47. Boo hiss. Whether good or bad news, guys, I believe 47 is a prime number. I don't think I could simplify anything further if I wanted to, so I'm going to have an I root 47 when it comes down to the quadratic formula. Let's just leave the discriminant like that for now. Let's dive into the quadratic formula. I'm going to have to clean some other stuff anyway, so let's do that. All right, x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This will now become x equals negative 3 plus or minus. Here's my I root 47. Again, I think it's a prime number, much less it can't divide by 4 or 9 or 16 or 25. And all divided by 4. That's a terrible all divided by there. All divided by 4. There's your final result. No fractions can reduce in this case either. And just a heads up, I mentioned before where a fraction could reduce if I had a 20 on the bottom. If this was a negative 32 or something, guys, I couldn't just clean these up and turn that divided by 4 and get 8 and 1. The reason is because this term would also have to have a multiple of 4 that I could divide by to make it happen. As long as there's a plus and or minus, you can't do that unless they could all divide. Every term with numbers outside of square roots could all divide by that. Anyway, this was a negative 3, and that's your answer. Okay, letter E, last one of these quadratic, and I think there are 3 more quadratics after this. So guys, this is a long video. I didn't know what to anticipate. I was hoping I could make it faster, but alas, I hope you're learning. All right, part E is definitely completing the square worthy. I'm going to subtract the 8 over, so I can find another value that does make this a perfect square trinomial. And once again, I see where this is going. I imagine all complex solutions are afloat here. 2 divided by 2 is 1. 1 squared is 1. That's what completes the square here. I add 1 to the left. I add 1 to the right. This factors down into x plus 1 quantity squared. And negative 8 plus 1 is negative 7. I will take the square root of both sides. Here I get x plus 1. Here I get plus or minus. Equals plus or minus. And I root 7. Hopefully you're getting really comfortable with the negative root 7 is I root 7. Always start with that if you can, and then check to see if you can simplify the positive square root thing. I can't. Subtract 1 over to this other side. We'll get x equals negative 1, the one I subtracted over, plus or minus I root 7. It's that simple. And honestly, guys, completing the square is better for this one. Not only is it less steps, but when you are... The quadratic formula automatically has a fraction. I mean, but when I clean it up, it won't. But then you got to work on the cleaning up portion of dividing these by the same number and such. And it can get a little weird. If you know completing the square and it's a problem that's meant for it, I would totally use it. All right, so there are 5 problems right there. I believe there are 3 more. They say use the quadratic formula. I say I'm going to use what I want, homie. And honestly, guys, all these look very completing the square-esque. They really do. Now, what I will mention is if you are going to use quadratic formula, you have to make sure that you're in standard form like this for this problem. I don't want to use quadratic formula there. I don't want to do a 4ac. This one has real number solutions to this thing. I just don't think they're rational. And here you're going to have to get this one in standard form as well, like that, if you're going to use quadratic formula at that time too. So make sure if you use quadratic formula, there it is. I'm going to focus more on completing the square. I think it's a little more foreign for my students. I want to get them to believe in the hype, that the hype's real, that you can use it. So I'm going to, anytime I can, I will, which basically means, do I have a 1x squared? Do I have an even linear coefficient? The answer to both are yes. All right, so here I'm going to subtract the 1 over. I get x squared plus 4x equals -1. I'm going to add a number. Let me give myself more space there. I'm going to add a number here that will complete this square. We did this. We did with 4x before. Divided by 2 is 2. Square that is 4. Only before I think it was a -4, right? So we get that. Factor this thing down. This becomes x plus 2 quantity squared. And -1 plus 4 is 3. So x plus 2 quantity squared equals 3. Let's take the square root of both sides. Hey, this is a real number solution set. There's no I involved. Don't just write i's out of thin air. You do that when you're taking the square root of a negative, and we're not doing that. Now, plus or minus is still involved here as we take that square root, now that this is just an x plus 2. And when I subtract 2 from both sides, I will be getting x equals -2 plus or minus the square root of 3. This problem resonates with our last unit that we did before we left for winter break as a class. This one is literally nothing new, a bit of a rehash of things, and I'm showing completing the square as often as I can. I'm not following these instructions. There's no reason you should be restricted to solving which way. What's better is if you can tell yourself which way you like the most based on a situation, and whenever I have a positive 1x squared, whenever I have an even linear coefficient, I will absolutely use completing the square. So here we go, in completing the square, this thing's already isolated here. I just got to add a certain number on the left, and then I'm going to add that certain number here on the right. And once again, it looks like this is going to be a real number solution set. In fact, all three of these might be. Oh, I don't think this one is. But all the other ones I think are. All right, -8 divided by 2 is -4. -4 quantity squared is a positive 16 divided by 2 square. That's the perfect square trinomial. That's what completes this into a perfect square trinomial. And then plus 16 over here leads me with factoring this down to x minus 4 quantity squared. And here I get a 43. I think it's one of them prime numbers, so that when I take the square root here, I can't do anything else with the root 43 other than leave it as a root 43. Unless I added wrong, which I don't think I did. So that becomes x minus 4 equals plus or minus the square root of 43. And when I add the 4 over, I will be getting x equals positive 4 plus or minus the square root of 43. And remember, these real number solutions does mean that when we graph, if we graph the y equals equation with a, I don't know, these would cross the x-axis somewhere at 4 plus root 43 and at 4 minus root 43. But the imaginary solutions don't happen to cross that x-axis. It's just a vertex. It's a vertex above or below or something like that, and it never actually hits it. That's what imaginary solutions do, whereas this solution we're looking at might do something like this. It might do something like that. It has two solutions, two ones we can see on the graph. All right, last one, number C. Letter C here. Not the last question of all, but the last of these solving quadratics. X squared plus 7 equals 4x. You know, if I do want to solve this using completing the square, I got to subtract the 4x over to this side, and I got to subtract the 7 over to the other side. And here I will be adding an unknown number. I think we should know it at this point. We just used the 4 before. It's a 4 again. Even though this is negative, this is positive after we square it. The difference is this factored to x plus 2 quantity squared. This is going to factor to x minus 2 quantity squared. This is a lot like, people are like, you're going too fast. This is a lot like part A in this last problem. I'm going too fast. I've spent an hour 23 minutes so far talking. And I still got another video to make. X minus 2 quantity squared equals -3. Take the square root of both sides here. And here we will be getting x minus 2 equals plus or minus I root 3. Back to imaginaries. They're made up. Add 2 to both sides, we get x equals 2 plus or minus I root 3. Kind of close to this answer here. This, well, I mean, this has an imaginary part, but That's negative 2 plus or minus root 3. This is 2 plus or minus I root 3. I don't know. Kind of close-esque. All right, those are the solving quadratic equations ones. Hopefully you got a nice overabundance of that. I know I did a lot more completing the square than quadratic formula. I do know that, and sorry if I didn't show you enough quadratic formula. It's just, it's a time suck if I do that too much. All right, the next problems that we have here are doing things with simplifying expressions with exponential properties, and I'm going to go as fast as I possibly can with this. I know that there's more than one way to do these problems. In fact, there are an infinite number of ways pretty much depending on what you want to do. I'm just going to talk about things where I'd say if I wanted to do it here, this is how I would. And that's all there is to it. If you're coming here to get some advice, then heed my advice and try and use anything that you can. I'll write up some properties on the side or down below or whatever that have to do with what I'm utilizing each time here. Okay. Now, they say simplify each completely with no negative exponents in answer. And that also means that any number bases here raised to some exponents we should be evaluating. Okay. This is yelling. You must show all steps that demonstrate mastery of rules, exponents, and radicals to receive credit. I agree. Especially in this distance learning format, it's hard to tell. There should be commas here. The Oxford comma as well. There should be, with distance learning, who's to say where you're getting your information? I want to make sure to know exactly what's happening here. I'm talking to my students when I say that. All right, so part A here, 16 to the 3/4 power minus 32 to the 4/5 power. This does not say 16 3/4. This is 16 to the 3/4 power. And what we're doing here is the equivalent, I'm going to write this property now, is if you have some base raised to a fractional exponent, it may, depending on what you want to do, it may be rewritten as the nth root of x to the mth power, like that. Now, you may either take the nth root first or raise that x to the mth power first. Either or is fine. It's okay, provided that you do it. So here, with the 16 to the 3/4 power, guys, I'm going to go ahead and rewrite that as the 4th root of 16 cubed. And then the 32, subtract 32 to the 4/5 power, I'm going to rewrite that as the 5th root of 32 to the 4th. Now, would you rather do 16 cubed, which is 16 times 16 times 16, and then take its 4th root? Or would you rather take the 4th root of 16 and then just raise that and then cube that? I'd rather do the latter. I'd rather take the 4th root first. The 4th root of 16 asks what number to the 4th power gives me 16. I gave my students a power table that they can use to kind of look at this here. That value is 2. So what I got to do here is I got to do 2 cubed there. When I take the 4th root of 16 and then I cube it, I'm going to take 2 cubed. And here, the 5th root of 32 is what I'm going to do first as well. And that's also a 2. We're going to take that 2 and we're going to raise it to the 4th power. So that becomes 8 minus 16. 2 times 2 times 2 minus 2 times 2 times 2 times 2. And that is negative 8. Very crowded area here. Sorry if I need to give myself more room down the line. But that's the property stuff that I just used right there. I converted it to this form to recognize what I do with it. Note that I'm not taking 3/4 of 16, which would have been 12. This number was not 12. It's a way different process there. We're not multiplying by it. We're not adding it. We are raising it to that exponent. All right, part B, 101 over 1001 to the 0th power times 27 to the 2/3 power. Next property, I want to write that any non-zero number to the 0th power is indeed 1. 0 to the 0th power is called an indeterminate. I don't think that we're going to be doing that in any of these really ever, but if you get tricked by it, just know that there's nothing you can do about it. I was saying I don't know what to do here. It's not a reducible fraction that I know of, but once this fraction, it's raised to the 0th power, so this whole thing's going to turn to a 1. It's going to turn to a 1 so much so that when you multiply 1 by something, the 1 is obsolete. I'm really just going to get rid of this. It's just there for show. All you have is 27 to the 2/3 power. And if you saw from the last problem that we just did here, guys, I'm going to take that here and I'm going to rewrite it as the cube root of 27 squared. Now the cube root of 27 is 3 and 3 squared is 9. This, for my students, guys, this is all in your power table. Some people should know how to take your roots and such or let your calculator help you. This is all in your power table for cube root of 27. What number times itself is 27. That number is 3. 3 squared is 3 times 3, which is 9. All right, letter C. X to the 4th raised to the negative 2nd power. over x to the negative sixth. Now, I'm a big fan of, if I have a fraction especially, getting rid of my negative exponents as fast as possible. And the general idea of negative exponents, as I write them with the properties here, is if I have some base raised to a negative exponent, that's equivalent to bringing the numerator value that it was into the denominator, making my exponent positive. So right here, what I'm going to do with this top thing, and there's another property I got to write down in a second, but automatically, just right now, I'm going to take this whole thing, guys, I'm going to move it to the denominator. This was in the numerator as a negative exponent. It'll be a denominator as a positive exponent here. So I'm going to take that. Let's change colors here. I'm going to take that, and now I know that in the denominator I have an x fourth squared. This thing didn't change at all because this is within a base in and of itself, and that whole thing's being squared. The negative second power became positive second power. Now this one in the denominator also has a negative exponent, and that's another property in and of itself, that when you have a negative exponent in the denominator, that becomes a positive exponent in the numerator. So I'm going to take that x to the sixth right there, I'm going to go ahead, or negative sixth, I'm going to move it up, and it's going to become x to the positive sixth. And I think that helps with a lot of things when it comes to kind of solving the rest here. All right, so positive exponents ahoy. We need positive exponents in the end, no negative exponents in answer, and I think that that was a good start. Okay, the next thing that I'm going to do here, whenever you have, it's not truly a power raised to a power, but it's a base with an exponent, and that whole thing is raised to an exponent. What you can do is take those exponents and multiply them together. Now, I won't get too deep as to why that is. I know I've done it for my students, and I'm sure a power hour probably has covered it somewhere, but I get to multiply the 4 with the 2. So that property says if I take something raised to an exponent and that whole thing is raised to an exponent, you keep the base and you multiply those exponents. Notice that that only happens for exponents. If I have 4 squared somewhere, guys, I'm not going to do 4 times 2. That is 16. But x to the 4th squared is indeed x to the 8th, not x to the 16th. I have x to the 6th on top, and x to the 6th divided by x to the 8th. Let's write down another property there. When you are dividing two items with the same bases, raised to some exponent, whether they're the same or different or invisible, you keep the base and you subtract your exponents there. So there are different ways that I go about doing this. Let me show you the raw form that I just mentioned there. I could take that and turn it into x to the 6th minus 8 power, which becomes x to the negative 2nd power, and they don't want negative exponents, so I'd be using this property here one more time, and I'd be turning it into 1 over x squared. And this is what some people might be doing going into this. What I tend to do at this juncture myself is I say that, when you're dividing here, you're basically canceling pairs of x's that are multiplying on top and bottom together. Now, there are 6 x's multiplying on top, there are 8 x's multiplying on bottom. If I cancel out all 6 x's on top and 6 of the 8 x's left on bottom there, 6 of the 8 x's on bottom, I will have no x's left on top, but I'm still left with a 1. Because when you just divide everything there, it becomes 1. And then on the bottom here, I still have 2 x's remaining, and that's the 1 over x squared. So it skirts past not writing the step, but it skirts past getting the negative exponent again and being confused whether that's on top and bottom. This thing still knows for sure that, this was 1 times x to the 6th, and now it's just a 1. And this was x to the 8th, and now it's only x squared. Either or, you're going to get the same answer. Now, these properties are kind of out of order as far as, I haven't done one property that I imagined I would have written a long time ago, but here, let me just write it, just because it's kind of next to this one here when we divided. What if we multiply two bases with two of the same base here with some exponents? You keep the base and you add the exponents in that case. We'll see if this arises at all. Okay, let's look at parts D, E, and F now, and I am kind of running out of room. I'm sure these properties got to go elsewhere in a second. Part D, I got to write another property. Part D, let me move my face. Let's start with that. An hour 33. Boy, am I moseying along. Part D, x to the 1/2 power times y to the 1/8 power, all raised to 16th, times the square root of x to the squared y to the 4th. Now, I personally am a fan of, when using variables, not using the radical form. I mean, personally, I'm an either or. I can use either way. When it comes to recognizing where my students have the least struggles when they've learned these properties, I think they really don't mind seeing the fractional exponents if they know how to convert it. And using this property here, we can do a rewrite of this square root and get fractional exponents out as a result. I ain't ashamed about that kind of look. What we have to know, though, is that a square root means the second root right here. And all these are technically raised to the first power if you really want to get to the nitty-gritty of how we rewrite this as a fractional exponent. And like I said, I'm going to be doing things the way that I would have been teaching them to my students. So here we go. Sorry, you got to follow along with that if you're following along with me. So here we go. I'm going to I'll do the other part next alongside this. So I'm going to leave this written the exact same right here. I'll leave this as x to the 1/2 times y to the 1/8, all raised to the 16th power. And we are multiplying this here by x squared times y to the 4th. And this is going to be raised to the 1/2 power. The square root of something is equivalent to raising to the 1/2 power, as you see in this property here. Now all of these are kind of in the same process that we got to do next here. This is another property that I got to write that says if I have a product inside of a quantity raised to an exponent, or a fraction actually, if I have a product or a fraction raised to some sort of quantity here, such as this here, the proper word is not distribute, but you will apply that exponent. You may apply the exponent into both of those guys there. And the same is true for a fraction. You know, we kind of saw the result of this when we were doing square roots earlier, if you remember. When we took the square root of some product, we split it up into a product of two square roots. Same thing goes with a power, as roots and powers really fall under the same order of operations vein. So raise this here to that exponent, and that'll be x to the m over y to the m, like so. Now we're going to be using this one, and we're going to be using it more than once. So right here, that 16 exponent will be applied to the x to the 1/2 and to the y to the 1/8. And then this 1/2 will be applied to the x squared and the y to the 4th. And I'll, to be frank, I think I'm going to be running out of room here in a second, so I can at least move the power table down a little bit. Just give me one brief moment here as I zoom out, and let's shift this a little bit. Little lot. I'll go back to them if I need them, or if you need them here. I am going to revisit one of these properties here in a moment. So this becomes, I mean, boy, if I'm to write all the steps here, this would become x to the 1/2, which is raised to the 16th, times y to the 1/8, which is raised to the 16th, times x squared, which is raised to the 1/2, times y to the 4th, which is raised to the 1/2. Now, the property I'm going to be using right now is how these things will multiply together. 1/2 times 16, 1/8 times 16, 2 times 1/2, 4 times 1/2. And don't be too disturbed with this thing with all these fractions here. Multiplying by 1/2, it means dividing by 2. And multiplying by 1/8 means dividing by 8. So what we're going to be doing here is 1/2 times 16, I'm going to take half of 16. And half of 16 is 8, so that becomes x to the 8th power. And then 1/8 times 16, 16 divided by 8 is 2, that's y squared. And then x squared to the 1/2 power there, once again, 2 times 1/2, that's 1, so that's x to the 1st power. And then this is y squared, 4 times 1/2, so y squared. Now we're still not done because there are multiple bits of x's. In fact, let's write them next to each other. That's x to the 8th times x to the 1st, and then the y squared times y squared. And now I get to use that property that I said we hadn't used yet, where multiply things with the same base, you keep the base and add the exponents. This will be x to the 9th power. I do 8 plus 1. This will be y to the 4th power. That's 2 plus 2. And you get x to the 9th, y to the 4th. Woo! Man, it's getting hot in my room. All right. Where's my camera? My camera's on a gimbal. It's not an actual tripod, but it's on a gimbal, and it seems to sometimes have a mind of its own. It looks like I was a little off center there. There we go. Maybe it's because I'm on the wrong side of the screen. All right, this part E here, I think this is where this thing that I mentioned before really does come into form in a nice way. If I convert this from the radical form to the rational exponential form here on this part E. So on part E here, I have x cubed y to the 4th. That's all raised to the 12th, and I'm taking the 4th root of that. If I convert that into this form here, that'll then look like x cubed y to the 4th to the 12 over 4 power. Now, 12 over 4 is 3. So this just becomes, this is a much easier problem than the last one, x cubed y to the 4th to the 3rd power. So we do what we did last time there. We take that 3 and we will, again, the proper word isn't distribute, but we are going to apply that into the 3 into the 4. And We do it through multiplication because it's the power raised to a power thing. So these will multiply for time's sake, as we've seen that already twice. I'm going to go ahead and say x to the 3 times 3, that's x to the 9th. Y to the 4 times 3, that's y to the 12th. And that's the simplification of that one. And the final one, as I argue over myself with which color I want to use, let's kind of use a gray. It's a little bit like the blue. Let's use a darker green. X to the 35th power to the 1/5 times the square root of x to the 8th. So here, with the x to the 35th to the 1/5 power, that is going to be multiplying. I'll be doing x to the 35th times 1/5 power there. I'm just writing that one step now because I'm like another step away on this. I'm a couple steps away on this one. The square root of x to the 8th means the second root of x to the 8th. Remember, that's an implied 2. So I could rewrite that as x to the 8 over 2 power. Seems like we're using this property a heck of a lot. Okay, I think we're kind of on the same stage now together here. 35 times 1/5 is 35 divided by 5. That's a 7. 8 divided by 2 is a 4. And I have x to the 7th times x to the 4th. That is x to the 7 plus 4. I'm just going to write that property there. X to the 7 plus 4, which is x to the 11th power. As my students, even as students of old, as you guys who are watching these videos from Altoona, Iowa, and Trenton, New Jersey, and such, as you get better at doing these properties here, at making sense of, and this was probably not all of them, but as you get better at doing these properties here, don't confuse them with old math that you always knew. What I mean by that is, I'm multiplying x to the 7th with x to the 4th, and I add these exponents here. Don't suddenly start saying that 7 times 4 equals 11. That, 7 times 4 is 28. Understand that exponents are their own different realm of talk. It has to do with how many times you multiply by something, and it really just does change, kind of how everything goes there. So make sure that you do recognize and note that these properties are of their own, and you should still remember how to multiply. You should still remember how to raise something to a power, like 2 cubed, and you should know how to divide. Just, don't lose sight of that, but keep these properties in mind, have access to them, and when you use exponents, there they are. Okay, I have one more set of problems here, problem number 8, and this is simplify each completely. The thing that's going to happen here, besides possibly rationalizing a denominator here or there, is that we have all these complex numbers with imaginary components, and we're going to have some imaginary number answers. It's just going to happen. But if we ever run into something that comes in the form of I squared, that'll turn into a -1. And this really is the crux as to how taking square roots of negatives even turn into an I in the first place. It has to do with I squared being -1. Not going to get deep into that, but anytime we have an I squared, it's not imaginary. It's actually a real number, and it is a -1, and that's what we're going to do. We're going to turn it into a -1. I's stay as I's. I squared's a -1s. Case in point, number 8, letter A, 7I squared. Let's use that last property we just saw, or from the last set of problems here. This is a product of 7 and I, and this squared goes to both the 7 and the I. So that becomes 7 squared times I squared. Well, that becomes 49I squared. Now, I'm not done because, like I said, when it comes to simplifying here, I squared is -1. So we turn I squared into -1, and 49 times -1 is -49. 7I, when I square 7I, I actually get a real number result. Yes, I do. There it is. There's a part D that you actually don't see right here. You probably wrote A, B, C, E, F, G. Where's your D? It's right there. There's letter D. All right. Part B. 3 minus 2I quantity squared. Now, there are a lot of ways that you can go. Well, I mean, listen, we could FOIL, but if you know your perfect square trinomial setup thing, like the A plus or minus A plus or minus B squared is A squared plus or minus 2AB plus B squared, you can work on it in this form here. I'm going to go ahead and show you this, whereas I also say if you're not sure what to do, you could rewrite this as 3 minus 2I times 3 minus 2I. Go ahead and FOIL it out. I'm right now saying this is something, if FOIL means multiply first, outside, inside, last. Don't worry, I'll have plenty of opportunities to do this. I want to show some other groups the perfect square trinomial revisit thing that some people might know how to do straight up. So, and this is a step I wouldn't ordinarily write, except for those who are just re-seeing this for the first time here. What I do is I square the A, so I get 3 squared Because this is a minus, I will be subtracting here 2 times a times b, and then I will be adding b squared. Normally I wouldn't write that step and I would just do it. In other words, hey, 3 squared is 9. Negative 2 times 3 times 2 is negative 12. So that's minus 12i, because there's neither. And then 2i squared, kind of like last time, you square both the 7 and the I. I square both the 2 and the I. That'll be 4i squared, like so. Now, if these were x's here, we would kind of almost be done. I would probably rewrite this term first, but these are not variables. And like I said, I squared is negative 1. So I'm going to turn this thing into 4 times negative 1, which is negative 4. So I'm going to have 9 minus 12i minus 4. And I can combine these two real numbers, 9 and negative 4, into a 5. That becomes 5 minus 12i. That becomes the complex number there, 5 minus 12i. That's your end result. So whether you did the foiling or expansion of a squared binomial here to make a perfect square trinomial, yada yada, we should end up with this result. This is a plus bi form, if you will. A is a real number, I is an imaginary. The bi is an imaginary number of sorts, and we have a complex number there. Sometimes they just turn into one number too, depending on how many terms there are and what you do. All right, part C. 4i over root 7 quantity squared. I thought we were going to have to rationalize the denominator, but now that I see that this is squared here, it looks like this will all go away. The squared here, recall this is a product. This is 4 times I, so we will square the 4, we will square the I, and in a fraction, we will also square the denominator there, that root 7. So in this problem here, I keep going back to this blue, and I already used it. Green, as we go write this thing out here, I will have, that's not green. I selected, there we go. I will have 4 squared times I squared times the square root of 7 squared. When you square the square root of 7, guys, you get 7 out. The square root of 7 says what number times itself, what's the number that we multiply by itself to give you 7? We're going to multiply by itself and get 7. I hate describing that thing. It sounds a little dumb. All right, 4 squared is 16. I squared is I squared. Root 7 squared is 7. I squared is negative 1. So we multiply 16 by negative 1, we get negative 16. This is negative 16 sevenths. We're going to leave it like that. A real number result. Negative 16 sevenths. Nothing to rationalize. It's a real number. All good to go. All right, part D. Let's add 9 minus 4i with 2 plus 3i. They put them in parentheses as to quantify this is a complex number, this is a complex number. Let's add them. But you know what? I now want to combine the real parts, and I want to combine the imaginary parts. I'm going to rewrite this now without parentheses, given the notion, of course, that the addition didn't change anything here. Plus 2 plus 3i, and nothing changed when I removed them. It might help when combining like terms to maybe put the 9 and 2 together, and the negative 4i and the 3i together. It might. For other people, they're probably fine there. And 9 plus 2 is 11. And negative 4 plus 3i is negative 1i, or just minus i right there. You might get, we treat I like a variable in that we can combine like terms with it. We treat I like a variable in that, when we square it, we get an I squared. The difference is, of course, when we square the I squared, it's negative 1, and this isn't a variable. It's not something to solve for. It's a modifier to help describe that it's an imaginary number. But otherwise, it's very variable-like when it comes to treating it. We only combine i's with i's, things like that. All right, 3 more problems, and then I am done. I will get this in under 2 hours. I feel a little accomplished with that. I'm kind of glad. Let's move this out of the way. All right, and this. 10 minus 3i minus 7 minus 4i. Now, complex number here minus complex number here. Well, that's fine. Just keep in mind one more time, though, of course, that as there are parentheses here, I can rewrite this stuff without parentheses, but now that this is subtracted, I will be subtracting this quantity here. Minus the 7 minus the negative 4i. Minus the 7 plus the 4i. Basically, the signs here switch. When I subtract a negative, it becomes addition. For sake of time and space here, I'm not going to reorder the terms, but I will combine like terms. 10 minus 7, guys, is 3. Negative 3i plus 4i is positive 1i, so that's 3 plus I. another complex number solution. Well, all these are complex number solutions, but a real and an imaginary together. All right, letter F is where I get to play the FOIL game with you guys. I have two binomials. They are not the same in any sort of way here, so I'm going to FOIL by doing first, outside, inside, and last. 7 times 5, that's 35. That's first. Outside, 7 times negative 2i, that's negative 14i. That's outside. Inside, I times 5, that's 5i. Last, I times negative 2i, that's negative 2i squared. I times I. Now I will combine like terms here in several ways. I'm going to still write another step with this one here, but I can combine these I terms right here together. Negative 14i plus 5i is negative 9i. Negative 2i squared is plus 2. See if you can connect why that is, knowing this part. I'm leaving that part to you. Okay. All right, 35 plus 2. I can combine those two. That's 37. So I'm going to get 37 minus 9i. Now, what these numbers mean to you at this point is irrelevant. The fact that you're just learning the process, I think, is enough, and then you can carry it into future things that you do with it if that ends up being the case. At the very least, it does explain the whole thing on taking square roots of negatives. All right, and the last one here, part G, 9 plus 2i times 9 minus 2i. By all means, please go ahead and FOIL. I, of course, want to reintroduce this to people who want to be in the know. You guys remember when you multiply a plus b times a minus b, you get that difference of two squares, a squared minus b squared? Well, that's what we're doing here. The difference is, and this is kind of neat. This is kind of neat. This is literally a plus bi times a minus bi. And you know what happens here? I'm going above and beyond here when it comes to writing. This is probably something I shouldn't be doing because I probably want my students to show more work, but I'm giving you kind of a know-how. This becomes a squared minus b squared I squared as those two multiply. But you know what I squared is? That's negative 1. So you know what this turns into? It turns into a squared plus b squared. It becomes a sum of two squares, if you will. And both of these become real numbers. So that b, in this case being a 2, and the a being a 9 means if I do this thing right, I don't even need to FOIL it all. All I need to do is just write that, sorry, I'm looking for a color. I just need to write that 9 plus 2i times 9 minus 2i, that equals 9 squared plus 2 squared. Literally, that's it. I got to check and see if photomath does something like that, and if so, I'm going to have to make this a no-no for my students because I can't let them photomath. 9 squared is 81, 2 squared is 4, and 81 plus 4 is 85. It's an all real number. It's a positive number. That's the end result. That's a good way to finish that thing off. Remember, of course, you could FOIL this thing. You should still be getting 85 because your imaginary should cancel, and then that minus 4i squared will become plus 4 still when all's said and done. All right, guys, that'll do it for this one here. That is everything that I've covered, and that was done in under 2 hours. I was hoping for an hour and a half, but you know what? I'm explaining stuff, and I sure hope that you learned something along the way. Description section down below, sure, can go back to any previous problems that you want to see, along with the PDF on there. I sure hope that helped. Please make sure that you leave a comment down below if you do have a question for anything as well, and I'll be here with more content down the line. Thank you guys for watching. Take care.